So this is Statistical Rethinking, second edition, chapter 13, question 13M3. Okay, so here's the question. And basically what we are doing here is we are running a model. And this model we saw earlier in the chapter, and in fact we also ran it in the previous two problems here. It's model 13M2 in your book. Okay. And so what we're going to do, whereas this model, so this is a hierarchical model where we have these hyperparameters for the intercept of tank. Maybe that's the wrong, yeah, this one right here. For tank, we have hyperparameters for the intercept that are normally distributed with mean A bar and sigma tank as the standard deviation of this hyperparameter here. Or, I mean, that is a hyperparameter of this, I don't know what you call it, the hyper distribution, maybe. Okay, so again, what this is going to do is it's going to estimate an intercept for every tank in our data set. So if this seems a little bit unfamiliar, then please go back and watch that previous problem. But we're going to replace this hyper distribution from a normal distribution. So I'm rerunning the model here. We're going to replace it with a Cauchy or Cauchy distribution. I'm not sure the best way to pronounce that. Okay, and that's the one change we're going to make. I guess there is an additional change. I think originally this A bar had a 1.5 standard deviation, and I'm making it 1 just to make it comport more directly with our Cauchy distribution here. So anyway, we're going to run those, and well, we're going to compare the alpha tank estimates between the two problems here. So I've already ran these models. It tells us that we may have some divergent transitions. Why, and can we fix them? And at least when I run this, I get no divergent transitions. But if I did, it would be because this Cauchy distribution is very fat-tailed, and so there's a lot of area out on the extremes that sometimes can be difficult for your Markov chain to explore. And so we could do some things to try to fix that. We could try, reparameterizing the model. We could try running it for more iterations. But I did not have that problem, so I guess bully for me. So we'll just ignore that. So now we're going to compare the A tank parameters between the two models. Okay, so there's just a lot of code here, and it's going to make a plot. But basically, I'm extracting the posterior distributions from my two models, and then I'm looking at the A tank estimates from those posterior draws, and I'm taking the mean of those estimates for each tank as well as the high probability interval for each tank in each model. Okay. Now, in addition to that, our model also estimated A bar and sigma tank, and from those, I'm going to create kind of the mean of the A tanks from the two models. I hope that makes sense. Okay. All right, so I'm going to go through and I'm going to plot. So I'm just plotting the estimates for each tank from model 2 over model 1. Okay, and then I'm also drawing the error bars. Okay, I think it's like the 89% credibility interval for each of those. Okay, for each estimate from each model. And then I'm also going to plot the mean of these A tanks for both models here. Okay, so this is what it looks like. Let me actually zoom in. Let me get the zoomed in version here, and then we'll zoom out later. Okay, so here we have. So every gray dot represents one tank, and its position on the x-axis represents its estimate for the normal prior, and its position on the y-axis represents its estimate for the Cauchy prior. Okay, and the red dashed line here represents equality between the two. Okay, So now what you see is that all these gray dots here, they basically lie right on the same line. In other words, the two models are giving us the exact, or not the exact, but very similar estimates, except for when we get out here to the extremes, right? And now the Cauchy distribution starts to have, allow much higher estimates, okay? So if we were to zoom out, this error bar here would actually go all the way up to, I think, 80 or something like that. Well, anyway, so it's a very large, or no, actually we're even missing a few data points. There's a few data points above this that I've cut off just to make these, the x and y axes scale equally. But anyway, but we get that the Cauchy distribution is permitting much larger values. Well, this makes sense because the Cauchy distribution, being very wide-tailed or fat-tailed, is of course going to constrain less, extreme possible values than the normal distribution is. So we should expect that high values in the data are going to have higher values being estimated or predicted for the Cauchy distribution than a normal distribution or normal prior. Okay. Now this big black dot here represents the mean tank or mean of tanks, and the probability distribution or the probability interval for both models here. Okay. So you can see that the mean distribution or the mean tank or whatever lies more or less on this red line. It seems to be skewed a little bit higher for the Cauchy. And if we go down and look at the Précis output, we see that that is in fact the case, right? So this is the Cauchy distribution, and it does have a slightly higher estimate than the other. So that's fine. So I think that's everything that the question asks us to do. But I want to also notice some things about the error bars here. So I'm going to go up and I'm going to zoom back out and get the full view of this posterior or these predictions here. Okay, so here we go. Okay. So you see that generally, as we move up and to the right, the error bars in both directions get bigger. But because the Cauchy distribution, or I guess correspondingly, the Cauchy distribution having allowed greater values also has greater error bars. Okay. Now this, I think, makes sense intuitively because as we have greater and greater, as an estimate deviates further and further away from the mean value, we should be increasingly uncertain of that value. Okay, I hope that makes sense. So for a couple of reasons. One is, well, okay, practically that is very useful because as we have more extreme values, we should be increasingly skeptical of them as being anomalous in the data set. Okay, but also we have less data that can constrain those estimates as we move out to these more extreme values, and so there is more uncertainty there. So those two reasons kind of work hand in hand. And there's something else that is interesting, possibly interesting. I'm really not sure, but that is that the error for the normal distribution of the mean tank, the black dot here, is greater than for the Cauchy. Now that seems, well, okay, it's being exaggerated here because of the difference in the scales. So let me go back up and zoom back in so that the scales are the same. Here we go. Okay, so that's a more fair depiction. But you do see that the error bars for the normal distribution are greater than for the Cauchy distribution. All right. Now I don't know if this is a general feature or not of this kind of a setup. Like for instance, if we had different data, if this would replicate, that pattern would replicate. And so I'm not sure that I really understand. Okay, if, on the assumption that it does replicate, I'm not really sure. I'm not sure that I understand why. And so if you have a good sense of this, then please direct me to a better answer. But my guess is that it has something to do with the increased flexibility of the Cauchy. And by flexibility, I mean its ability to entertain a broader range of potential values. And the way that I think this may be working is that the increased flexibility of the Cauchy allows a better, a more exact fit to the data. Okay, and so because of that, the estimates from the Cauchy are less variable than for the normal. Why? Because the normal has had to, well, has constrained the estimates, and so it's going to fit worse to each particular data point. Okay, so that is my, full disclaimer again, that is my guess. I'm not really sure, and if you have a better answer, then please direct me to that. Okay, anyway, I think we will call that good.